Okay, now we're going to look at the stereochemistry of a Diels-Alder reaction. We're still in 17.7. It's a very meaty section in the book. If we look at the stereochemistry, if we have substituents on the diene or the dienophile, the stereochemistry is retained in the reaction. And I'll show you what I mean by that. So you can see we have two methyl substituents on our diene, and we have two cyano substituents on our dienophile. Here the substituents are cis to each other. When we have reaction, our substituents will remain cis to each other. Okay, and so we get in the habit of numbering, so you can see where everything belongs. There's our product. So we are going to retain the configuration of the starting dienophile. The same is true for the stereochemical relationships on the diene. So for example, if we start with the following diene, there's our diene. We can see that the alkenes have an EE configuration, where the highest priority substituents are on opposite sides of the double bond. If they were on the same side, they would be Z. When we rotate this into the S-cis conformation, we have to maintain that E stereochemical relationship. This would put one methyl group here, and the other methyl group here. These alkenes are both E. Then when we add our diene, our dienophile, we have to maintain the stereochemical relationship between the methyl groups and the stereochemical relationship of the alkene of the dienophile. So remember, our base is always going to be cyclohexene. So it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, Typically, so here we have our product and there are two rings. This is a bicyclic. When we draw the bicyclic, we want to keep the rings in the plane. For reasons that I'll explain in a minute, this ring should be pointing down. So what this means is that the hydrogens, so if we keep the ring planar, the hydrogens at carbons 5 and 6 should be pointing up. Now let's deal with these methyl groups. They have to be cis to each other. Okay, so they will also be up. When you have groups, if you draw an imaginary line here, okay, these will be up, the methyl groups. When they are pointing to the inside like this, they will be down. Okay. In this case, because the ring itself has to be down, we're going to draw the hydrogens as up. I'll explain this effect when we look at another stereochemical relationship. Let's just do another example and I'll see if we can make it a little bit more clear. Okay, here we have an EZ alkane. This one is E alkene. This one is Z. When we rotate into the S-cis conformation, we have to maintain this relationship. Okay, EZ. So what you are going to do, this position is the out position, so this methyl group will be up. This position is the in position, so this methyl group will be down. It is pointing in. Okay, there's our dienophile. 1, 2, 3, 4, 5, 6. The product needs to have our base cyclohexene and then the ring. This was 1, 2, 3, 4, 5, 6. Again, I'm going to go through this, but the ring should be pointing down. So we need to make the hydrogens here at the bridge pointing up. The methyl group on carbon 1 is pointing in, so that will be down. The one on carbon 4 was pointing out, so that will be up. Alright, so in that previous example we drew a bicyclic product. Bicyclic is when we have two rings fused together. Okay, let's look at another example where we're going to form a different type of bicyclic product. So there's our diene. Here's our dienophile. 2, 3, 4, 5, 6. So, our base is a cyclohexene ring. 1, 2, 3, 4, 5, 6. On carbons 2 and 3, we have a methyl group. Now, carbons 1 and 4 are connected by 2 carbons. And just to show some three-dimensionality here. Okay, so they're connected by these 2 carbons. 5 and 6 have ester groups attached to them. The ester groups need to be cis to each other, and they will point down. Okay, so the esters point down, and the bridge points up. If we were to redraw this, we would put the cyclohexene planar. Okay, 1, 2, 3, 4. Here's our bridge of 2 carbons. This is 5 and 6, and the ester groups would be pointed down. This down configuration is called the endo configuration, and it is favored because we have orbital overlap. So let's look at another example. Here we have cyclopentadiene plus our anhydride, which is the dienophile. If we count 1, 2, 3, 4, 5, 6. So, we make our cyclohexene base. 1, 2, 3, 4, 5, 6. Put our anhydride ring on. Okay. We need to draw the bridge, which is only 1 carbon now between carbons 1 and 4. And we need to show that we have hydrogens on positions 5 and 6. The ring will prefer to be pointing down. So instead of drawing dash wedges here, we will just draw the hydrogens as pointing up. If we translate this so that we have our cyclohexene ring here in the plane, 1, 2, 3, 4, 5, 6. Here we have a single bridge. And our ring pointing down. And the hydrogens are up. Again, this is the endo conformation. So why do we prefer the endo conformation? Why? Well, let's just break down another example and look at this. We have cyclopentadiene again, plus our dienophile. 1, 2, 3, 4, 5, 6. Here's the cyclohexene base. 1, 2, 3, 4, 5, 6. The 1 and 4 can be by a single bridge. Okay, for the endo conformation, the cyano groups are pointing down. This will equal this. If we were to make the exo product, so this is endo, the exo product would look like this. Again, we have our cyclohexene base. And in the exo product, the substituents, they are pointing up with the bridge. Okay, here in the endo product, the substituents are opposite the bridge. Let's just make this into the planar representation. Okay, so let's look at orbital overlap to find out why this is disfavored and this is favored. Okay, so we're going to favor the endo. Okay, so if we look at cyclopentadiene, we know that the electrons are evenly distributed throughout these 4 carbons. When we add our dienophile, we can have secondary orbital overlap if the substituents are facing in the direction shown. As a result, the endo conformation is preferred. In the exo conformation, you don't have these secondary interactions. They're too far apart. So let's look at the interacting molecular orbitals. Here's our cyclopentadiene. As before, when we wrote down the highest occupied molecular orbital, it looks like this for the diene. And for the dienophile, the lowest unoccupied here, okay, if you remember, this was the double bond we were looking at. Okay. Let's just draw a p orbital for the carbon substituent. Okay, so this is the LUMO of the dienophile. This is the HOMO of the diene. Okay. We want to interact, I'll show you in blue, okay, where we have this interaction here and this interaction here. When we are in the endo conformation, as shown here, we have secondary interaction shown in yellow. Okay, so there are secondary orbital interactions. In the endo conformation, which I'll draw, in the exo conformation, you do not have these interactions. So, let's draw the cyclopentadiene again. Okay, here's our cyclopentadiene. Now I'm going to draw the exo conformation. Okay, this is where you have the interaction, okay, between the diene HOMO and the dienophile LUMO. The blue shows you where you get the Diels Alder product. What you can see when the substituents are in the exo conformation, okay, so this was endo, you have no secondary orbital overlap. So this is why the endo conformation is preferred.